Some people say that math people do vectors differently than science people. It's not really different. All right, so 6.3. And we're talking about everything in chapter 6, we're talking about in the plane. Next semester we'll talk about 3D vectors. So vectors in space. But right now we're in the plane. And just kind of bottom line, everything that we do today has to do with turning vectors into little triangles. And tomorrow we'll bring back in the angles and the trigonometry a little bit with vectors. But everything that we're thinking about with vectors has to do with turning them into little triangles. So a vector, first off, what is it? Something that has direction and magnitude. So, some examples of things that are vectors. We could think of position as a vector. We're 2 feet this direction from the origin. Velocity would be a vector. We're going 20 miles an hour that direction. So we need to talk about how fast we're going and in which direction. Force would be a vector. We're pushing with 20 pounds horizontally. So that would be, that's another example of a vector. So we need to know the direction and how strong, how fast, whatever. We need a direction and a magnitude. We usually draw them. We think of them, the book calls it a directed line segment. So we represent them as arrows. So if I draw a vector, I'm going to draw a vector here. So that would be a picture of a vector. And I'm going to put some points. It goes from point P to point Q. We call point P the initial point. Or the tail. So that's where we start. And we call point Q the terminal point. So we go from the initial point to the terminal point. So a lot like we talked about with angles, where we have the initial side and the terminal side. And we would call this vector PQ with kind of a half arrow over the top. In your book, they show vectors as bold letters. But it's hard to write bold, so when we write them, we'll use the little arrows. And we'll do it a couple of different ways. So in print, in your book, they show vectors as bold print letters. The magnitude of a vector is the length. So when we talk about the magnitude, we're talking about the length. And we would write it as PQ. We use double bars around the vector to show the magnitude. And sometimes sometimes you'll see it this way. Usually in our book they use the double bars. Some books you'll see a single bar. When I learned vectors, we always just use the single bar. This means the magnitude of the vector, the length of the vector. And we find the length using the distance formula. So if we know the coordinates of P and Q, we can use the distance formula to find the length. And the distance formula comes from where? What's the distance formula based on? Pythagorean theorem. So we're turning this into a little triangle. And we use a distance formula to find the length of the hypotenuse. The distance formula comes from the Pythagorean theorem. All right, we good so far? All right, vectors are equal. Yes? We'll do an example. We'll write it down next. Vectors are equal if they have the same magnitude and same direction. So it doesn't matter where they're located, as long as they have the same magnitude, as long as they have the same direction, we call them equal. Now folks, electronics, they need to go away, please. So that's how we tell the vectors are equal. They have to have the same magnitude, they have to have the same direction. I can locate them anywhere in the plane, as long as they have the same magnitude and same direction, they're equal. All right, questions so far? All right, let's do an example using some of these ideas, and we'll write down what the distance formula is. So let's say we have V is from the point 0, 0 to 4, 5, to the point 4, 5. And U, vector U, is from the point 2, 3 to the point 6, 8. We want to show that U equals V. So when we want to show that these two are equal, we want to show that they have the same magnitude, they have the same length, and they go in the same direction. So let's find their magnitude first. Magnitude of U equals. So distance formula, the way that you usually see the distance formula is if we call this point x1, y1, and this point x2, y2, the distance formula is going to be the square root of x2 minus x1 squared plus y2 minus y1 squared. And that's just the Pythagorean theorem. This is the length of one side of the little triangle, the length of the other side of the little triangle, and we're using the Pythagorean theorem. So for vector u, that's going to be the square root of 4 minus 0 squared plus 5 minus 0 squared, 5 squared. And that gives me the square root of 41. And I'm just going to leave it like this because all we need to see is, are they equal or not? And the magnitude of vector v is going to equal the square root of 6 minus 2 squared plus 8 minus 3 squared, square root of 41. So they have the same magnitude. How are we going to tell if they're going in the same direction, if they're in the same direction from the information we have here? What's that? Positivity or negativity, and what do we, so let's be a little more specific. Points are positive or negative, and so we know that they're in the same quadrant, right? What was it? Slope. Let's look at the slope of these vectors. If they're the same length and the slope is the same, then they're going in the same direction. So the slope of vector u is y2 minus y1 over x2 minus x1. Slope of vector v is y2 minus y1, 8 minus 3, over x2 minus x1, 6 minus 2. So same slope. So that tells us that u equals v. They have the same magnitude, and they're going in the same direction. So questions there? All right. Next thing we need to talk about is component form. And like we had with angles, we have a standard position for vectors. So our standard position is if our initial point is at the origin and our terminal point is just somewhere else. So we call this standard position. And if this is vector v, our initial point is at 0, 0. And we're going to say that our terminal point is at the point v1, v2, just some point. And v1 and v2 are the coordinates of that point. We write v, we say v equals in these angle brackets, v1 comma v2. So these are kind of like coordinates. We call this component form. And v1 is the x component, and v2 is the y component. So we can write vectors with a little arrow, or we can write vectors as an ordered pair, an x and a y with the little angle brackets. We call this a component form. And if v is not in standard position, v is from x1, y1, some point, to some other point x2, y2, then we say v equals x2 minus x1 for my x component and y2 minus y1 for the y component. And the way I think about this is terminal minus initial. And this just tells us how far are we moving from x1 to x2, how far are we moving in the x direction, how far are we moving in the y direction. So the component form tells us how far do we move in the x, how far do we move in the y. And we find that by terminal minus initial. So we call this with angle brackets, we call this the component form. And component form makes it really easy to find our magnitude. So the magnitude of v in component form, v1 comma v2, is just the square root of v1 squared plus v2 squared. One side of my little triangle is v1 units, the other side is v2 units, and we can use this to find the length of the hypotenuse, the magnitude. And we write the magnitude, so we would say the magnitude of v equals the square root of v1 squared plus v2 squared. So the double bars means magnitude. All right, we good there? So a lot of basic terminology, not a lot of calculation, not much calculation in the stuff we're doing today. A unit vector. has magnitude 1. And the 0 vector and we write it as a 0 vector is the vector 0, 0 has magnitude equal to 0. And be careful, the 0 vector does not equal the number 0. One is a vector, one is a number. Vectors are different than numbers. The 0 vector is a vector with no magnitude. All right, we good so far? All right, let's do another quick example. We'll find the component form and the magnitude. So let's say our vector v is from the point 2, negative 4 to 5, 7. We want to find the component form and magnitude. So in component form, we want to do the terminal point minus the initial point. Make sure you do it in the right direction. So terminal minus initial for the x coordinate, I'm going to do 5 minus 2. And for the y component, I'm going to do 7 minus negative 4. And I get the vector 3, 11. So that would be the vector in component form. And what this is telling me is from 2 to 5, I'm going 3 units in the x direction. And from negative 4 to 7, I'm going 11 units in the y direction. That tells me in my direction. And then the magnitude of v, once we have the component form, that's really easy. The square root of 3 squared plus 11 squared. And when I calculate that out, I'm just going to leave it written as square root of 1/3. So component form and magnitude. All right, we good there? Now on the sheet that I gave you, it lists a bunch of operations. Yes?
Do we have to memorize this first place?
Memorize.
Like the different formulas, I guess?
Yes. They're really not. They're not really formulas.
Yeah,
but how they work. Yes. The sheet that I gave you. And on the sheet that I gave you, it gives you the operations with vectors. Basically, it's telling you how to do arithmetic with vectors. It's just like normal arithmetic. So we can change the order, and we can still add them. We can distribute if we multiply by a number. All of those rules for adding and subtracting. It's just like normal arithmetic. It's just kind of reminding you the rules for normal arithmetic. For adding and subtracting, the rules for vectors are the same as normal arithmetic. When we talk about multiplying vectors, sometimes the rules change when we multiply vectors, and we'll multiply vectors in a couple of different ways. But we won't get to that for a little bit. All right, so our vector operations. Vector operations just tell us how we add and subtract. So if u is the vector in component form u1, u2, and v is the vector v1, v2, to add these two, u plus v, I just add the components. u1 plus v1 is my x component, and u2 plus v2 is the y component. So I add the x components, add the y components. And when we're talking about vectors, we call real numbers scalars. But we don't say real numbers, we say scalars. So k times u is just k times each component. And geometrically, this is just the vector that is k times longer than u. So we're just changing the length. And if k happens to be negative, then it turns the direction around as well. And geometrically, we add vectors head to tail. So if these are my axes, this is y, this is x. If that's u, and this vector is v, the green vector here from head to tail is u plus v. So I start here, go to here, end up here, and the result is I start here and end up there. So geometrically we add head to tail. All right, we good there? Okay. So if we want to subtract, so if we have v is the vector v1, v2, negative v is just the vector in the opposite direction, negative v1, negative v2. So u minus v is the same as u plus negative v. And that's going to be, we subtract the components. u1 minus v1, u2 minus v2. So to subtract vectors, we just subtract their components. And geometrically, we subtract tail to tail. So if I have this as vector u, and this is vector v, the vector u minus v would be that vector. And that is because I can take v and turn it around backwards here. So that red vector is negative v. So I'm adding u to negative v here. So u minus v would be this vector here. We subtract vectors tail to tail, or we subtract their components, component by component. Yes. It does, no, it always works. So the fact that it looks like a right triangle just is a coincidence. So it doesn't matter how long each vector is, this technique will always work. And we can always do this in component form. All right, yes? So what I did here was we wanted u minus v, so I can take u and then take v and turn it around. And that tells me I start here and end here. Okay? They always start at the tail and end at the head when you add them. Okay. And I'm just going to go back here really quickly. So that's so u plus v, so I'm starting here. I went to here and then I'm adding v, so I end up there. That's how I got the direction there. Same thing here. So this minus v, so I start here. And right there. Other question? Most of what we will be doing with vectors is in component form. I want you to be a little bit familiar with kind of looking at them graphically. Most of what we'll do is in component form. All right, so last thing I want to do is a quick example with doing some of these operations. So let u equal the vector -5, 2, and v is the vector 6, -3. And let's do three things. Let's find 4u. So to find 4u, what do I do? Multiply each component of u by 4. So I multiply the x component by 4 and I get -20, and multiply the y component by 4 and I get 8. There's 4u. So the vector, same direction as u, 4 times as long. How about u plus v? I'm just going to add the x components and add the y components. So -5 plus 6 is 1, and 2 plus -3 is -1. Yes? Hmm? Right, so we could turn it around. Yeah, so 6 minus 5 is the same as -5 plus 6. Yeah. And then finally, let's do 2u minus v. So this tells me to multiply the components of u by 2 and then subtract the components of v. So we just do it component by component. So 2 times -5 is -10, plus 6 is, minus 6, -16. 2 times 2 is 4, minus -3, 7. So I just do whatever this operation tells me to do, component by component. So this will be the kind of thing that the homework asks you to do. There's some that ask about the graphically drawing vectors, that kind of thing. Mostly we'll be working with components. And on any of these, if it helps to write it out, sometimes if it's more complicated, I do. So this would be, I could also write this as 2 times -5, just showing what we did, minus 6, and my y component would be 2 times 2, minus, it's telling me to subtract, -3. We can always write it out and then simplify later. So it's fine to write it out step by step. All right, questions? Okay. There we go.